All right, everybody, this is the start of Unit 2. This is going to be both Units 2.1 and 2.2, quadratics and complex numbers. So I know we spent a lot of time in our mathematical careers with quadratics. Let's refresh our memory on complex numbers. So complex numbers take the form a plus bi, where a and b are real numbers. The complex number has two parts. This is A is the real component, and B is the imaginary component. If I want to add or subtract complex numbers, I combine like terms. And if I want to multiply, I distribute and simplify. Now remember what I represents. I represents the square root of -1. That's a non-real number. That's why we call it an imaginary number. What ends up happening is if I were to square this number, I would get I squared, and that would equal a square root being squared, or -1. So this is really the big idea here. When I multiply, I will end up with I squared terms, but when I end up with an I squared term, I have left the realm of imaginary numbers and I return to real numbers. When we divide, really the issue we have is that if I have an imaginary number in my denominator, I have a square root in my denominator. So in order to get rid of that square root, that imaginary number, I multiply by the complex conjugate of the denominator. I multiply both the numerator and denominator by that value. That is a mathematically legal move because effectively we're multiplying a numerator and denominator by the same thing. Anything divided by itself is 1. So that's a refresher on our complex numbers. Let's talk a little bit about quadratic forms in general. Now, our book refers to this as standard form, but more often we will call this vertex form. And what you can see here, vertex form involves a few constant values. We can see here, we can see here that this vertex would be h, k. We can see that the vertex form gets its name because the vertex is really easy to identify. The only thing we have to be careful of is if whatever we are doing to x inside the parentheses, that component, that say in this case x minus h, we switch the sign to identify that vertex. So in this problem, we are given f of x equals the quantity x plus 3 squared plus 1. They ask us to find the vertex, as well as some other features. The vertex here is staring at you. It is going to be the point -3, +1. Again, we flip the sign from what we see inside the parentheses for our x value and keep what we have on the outside as our y value. The intercepts will occur when the quantity equals 0. So if I said 0 equals x plus 3 squared plus 1, I would have -1 equals x plus 3 squared. Now, while we just talked about taking the square root of a negative number, creating an imaginary number, when we graph, we are basically graphing real numbers. So there are no x-intercepts here. We'll see that when we graph. The y-intercept can be found by plugging in 0 for x. If I were to do that here, I would have the quantity 3 squared plus 1. That's 9 plus 1, or 10. The axis of symmetry is the line that cuts this graph in half. It goes through the vertex, and it is an x equals statement. So our axis of symmetry here, sorry, let me write that out. Axis of symmetry is x equals -3. The domain for any quadratic will be infinite. It will go from -infinity to infinity. And our range depends on the vertex. It depends on the y value of the vertex and the direction our parabola opens. In this case, our parabola will open upwards, so our domain will start at +1 and go to infinity. I'm going to go ahead and graph this here. I'll give you a quick refresher on this graphing process. Our vertex is at -3, 1. So -3, 1 will go to the middle of my graph. Our function here was x plus 3 squared plus 1. So we are going to use symmetry here. I'm going to plot -4 and -5 along with -2 and -1. Quadratics are symmetrical, so anything that happens, when x equals 4 will also happen when x equals -2. Whatever happens at -1 will match at -5. I can find these values by plugging these quantities in. If I were to plug in -2, I would have the quantity 1 squared plus 1. 1 plus 1 is 2. If I were to plug in -1, I would have -1 plus 3, which is 2. 2 squared is 4. 4 plus 1 is 5. So those 5 points will be the 5 points I plot for my graph. 1, 2, 3. We're going to have our vertex here at -3, +1. Our next 2 points that are symmetrical to one another at -4, 2 and -2, 2. And our final 2 points at -5, +5, and -1, +5. We'll draw in our familiar quadratic shape here, that U-shaped parabola, and we are done. Maybe seeing that graph allows you to see that range make a little bit more sense. We start at y equals, I'm realizing I miswrote that. Y equals 1 and goes on up to infinity, right? Our y values start at 1 and go up. Here, what we call standard form and what our book calls general form, you can see is listed as ax squared plus bx plus c. Let's see what you remember. I recommend you guys pause the video right now and try to work through this problem. Find all those key features, the axis symmetry, intercepts, and domain and range. I will return here with this worked out. So let's take a look and see how we did. One thing you may not have remembered was how we find the vertex from our original standard form equation. What we use is this quick formula, -b over 2a. That gets us the x quantity, and in order to find the y value, we take -b over 2a and plug it into the function. So I found my vertex to be at the point -1, 2. That -1 came from that -b over 2a, and the y value came from just plugging in -1 in for x. The y-intercept, plug in 0 for x. The axis of symmetry has the same quantity as the x value of my vertex. The domain is infinite, and if you're struggling with the range, I would say save that for after you've graphed. You can see my graph is over here on the right. I set up my table of 5 points with the vertex here in the middle. Working out from there, I was able to use symmetry on either side of the vertex to fill in some key points. What you may notice from your graph is that the x-intercepts do not occur at a nice easy quantity for us, so we'll have to solve. I decided to move this into vertex form. I knew my vertex was at the point -1, +2, and that the a value, the leading coefficient, was negative, so I borrowed that. I set that equation equal to 0 and solved for my x-intercepts here at -1 plus root 2 and -1 minus root 2. Let's turn over to the second page and refresh our memory on a couple formulas. The one formula that we see in quadratics all the time is the quadratic formula. We can solve any quadratic, whether we have real or imaginary roots, using this formula, and it looks like this. The opposite of b plus or minus the square root of b squared minus, 4ac, all divided by 2a. Now you may be wondering, what are these a, b's, and c's? These come from what we will call standard form. They are coefficients from a quadratic form like you see here. Again, this is used to find solutions to any quadratic function. Part of the quadratic formula that we use is known as the discriminant. It is b squared minus 4ac. It is the stuff under the radical, and we can use this for a few different purposes. If this quantity is positive, we have two real solutions. If this value is 0, we have one real solution. And if this quantity is negative, we have two imaginary solutions. We also know that if this quantity is a perfect square, we will have rational roots. In other words, roots that can be written as a fraction containing only real numbers. If it's a non-perfect square, we may have to simplify our square root, but our roots inevitably will be irrational. They will involve a square root. What I'd like you to try at this point is try to work your way through these application problems in our notes. There is one coming from our textbook that concerns a model situation where there's a few questions to answer. And then there's a couple word problems. So I'd like you to pause this now. I will walk through these briefly in just a minute, but I really would like you to try these on your own. All right, let's see how we did on these application problems. So in the first one, there's a multi-step problem here that we're working through. We are given a formula that we're working with. Negative 0.01x squared plus 1.18x plus 2. And always worthwhile to know what this is represented. F of x is the height. Let me use a different color for that. F of x is the height, and the input, the x value, is the horizontal distance from the impact of the foot. So our x coordinate here will be our horizontal distance from where the player kicked the ball, and our output, our f of x, or our y value, will be the height of the ball at that horizontal distance. So in part A, they want us to find the maximum height and how far from the impact it occurs. That's just a fancy way of saying find the vertex. We can use a couple different ways of doing this. Negative b over 2a, in this case, would be negative 1.18 divided by 0.01, or negative 1/50th. When it's all said and done, the x value of our vertex ends up at 59. We plug in to find our y value of 36.81. Certainly one here where we might want to use our graphing calculator. Part B asks us, how far must the defensive player, who is 6 feet away from the point of impact, how high must they reach? In other words, if this player is 6 feet away horizontally, how high vertically must they get to intercept the ball, or intersect it rather? We plug in 6 into the formula and find they must be 8.72 feet high. Part C asks us, if the ball is not blocked, how far will the ball go? Really, it's asking us What will the horizontal distance be if the height is 0? My apologies, I wrote that coordinate backwards there. Let me adjust that. Our coordinate here would be an x-intercept, so our height would be 0. In other words, our y value, and our horizontal distance would be 119.67 feet. So the x value here is a horizontal distance traveled, and the y value, 0, tells us that we're looking for an x-intercept. Part 2 here, they ask us to look at all pairs of numbers whose difference is 10. You can see here I used x minus y equals 10. Find the pair whose product is as small as possible. So this is my pseudo equation. I solved one equation for x and replaced x with y plus 10. This formula is a function that represents the product where the input is the y value, the one of the two terms that we are multiplying together. Well, I know that this factored form that I'm highlighting here would have x-intercept at -10 and 0. And we can use symmetry. We know that the vertex is halfway between those two x-intercepts. The vertex would occur at -5. I can find my x value by using y plus 10. So -5 plus 10 gets us to 5. We multiply those together and get -25. So the minimum product would be -25. The numbers we would use to get there are -5 and +5. On example 3, this is a fencing problem. We know that the perimeter of a rectangle is 2w plus 2l. We set that equation equal to 100, the amount of fence we have in the problem. We are looking to maximize the area, so I will need to solve my first equation in terms of one variable so that I can create a function that is useful. Again, we can use symmetry. We know that the function on your screen now would have zeros at 0, 0, and 50, meaning its vertex would occur halfway between them at 25. I can identify my w as 50 minus that same 25. So I end up with a dimension of 25 by 25 for an area of 625 yards squared. And we are done.